with Jane Hayes discussing error, leakage, and wasted time in sensitivity analysis of requirements consistency checking. Thanks.
Okay, thank you, Colin. So I'm Jane Hayes from the University of Kentucky, and on behalf of my co-authors, Yann-Gaël Guéhéneuc, Wenbin, Mirek, Truszczynski, and Giuliano Antoniol, it's my privilege to talk to you today about our work on air leakage and wasted time. So I don't have a slide on Luxembourg or Kentucky, but I was thinking about it, and we actually do have sort of our own version of royalty, which would be the University of Kentucky Wildcat basketball team. And so this would, I guess, perhaps make our Grand Duke Coach John Calipari. So what I'll be discussing today is basically introducing and motivating the problem to you all, then talking to you about how we modeled error leakage and wasted effort, discuss our sensitivity analysis and results, touch a little bit on prior art, and then wrap it up with future work. So, as we all know, software is ubiquitous. We use it in our everyday lives. It's an important part of society. Unfortunately, though, software doesn't always have the highest quality or the level of reliability that we would like. To address that, as researchers and practitioners, we apply many different processes, methods, at various different phases of the life cycle to try to address this. These could be quality assurance methods. These could be requirements engineering methods, coding methods, testing methods. I show 3 examples here of some different methods or processes that might be applied. On the far left of the slide, we have basically the recovery or discovery of a fault taxonomy using some clustering techniques. In the middle, we have feature location, maybe to assist someone as they're debugging code. And then on the far right of the slide, we have traceability. What you notice in common for all of these processes or methods is that they're basically a sequence of steps or sub-processes that are accomplished by some techniques. Actually, and this is very common in our field. As researchers, we've done a fairly good job at looking at the quality of each of these individual steps or techniques in isolation. And we have worked to, quote unquote, optimize, I'll say quotes because I don't mean it in the sense of this setting, to optimize recall, precision, accuracy, and these types of things. However, what we haven't really done is thought about the combination of these individual techniques into overall processes or methods, and think about the effect or the impact of errors that may be introduced in an earlier step and how that basically leaks into subsequent steps and then unfortunately leads to erroneous results at the very end of the process or method, meaning that our poor human analyst who's using the results of this process or method is basically caused extra work or unnecessary effort or wasted time. So before we move further into some other thoughts on this, how do other industries deal with this? Well, the hardware industry has figured this out, right? So you could certainly have the case of error leakage between these different steps, or in fact, in the case of one of the related works that we looked at in this paper by Ni et al., they were actually interested in whether or not you could have power leakage due to process variation, due to problems in these individual steps. In the hardware world, they basically have a quality check at the end of each of these steps or sub-processes. And if a particular hardware part does not meet specs or exceeds some limits, they'll just discard that part. In the software world, though, not only do we not typically have a person that sits in between each of these different steps or sub-processes, sometimes even at the very end of the process, our humans who are using the results of our outputs, say feature location, they don't even necessarily check that the information given back by the feature location method was correct. They assume that it's correct and they move on to perform that work. To complicate matters further, it's not the case that there's just one technique one size fits all for each of these different steps that we want to accomplish. So there's certainly many, many different types of techniques that you might choose to perform retrieval of some sort. Information retrieval techniques, LSI, LDA, and so on. It's not even the case that there's just one accepted stemmer if you're performing stemming. And in fact, it's not even necessarily accepted that you want to do stemming or that you want to do stop word removal. So, in fact, I wanted to mention here that just last week I was reading a conference paper by Giuliano and some of his colleagues on boilerplate checking of requirements, a tool that they have called Rubric. And there, they did a study to basically look at putting together a configuration for a rubric and looking at all the different techniques that they might apply and how they might configure those. And even that, for rubric, became a very large problem. So, and I guess I should also mention that, of course, none of these techniques are being performed in isolation. Just as in Lionel's talk earlier, he talked about those controllers being used in all different environments and how they had to think about how to configure the parameters and set the parameters so that those controllers could work best in the given environment. Guess what? We're not using any of these techniques in isolation. We're running these techniques on specific data sets or for specific projects and in different domains. So, with these error leaks that I've mentioned and these uncertainties having to do with your environment, your project, and so on, how is a researcher or practitioner to decide what techniques they should use at the various steps of these processes? And how do we know which factors are going to influence the final quality of our process? We believe that search-based software engineering can support this design process by doing a sensitivity analysis to help guide our selection and to minimize this error leakage and this wasted time that I mentioned. And this is a first step toward that goal, basically an exploratory sensitivity analysis. So this will be the running problem throughout the paper, our running example, so let me specify the problem here. We're interested in performing consistency checking on temporal requirements. By temporal requirement, basically anything that has to do with time, but think of something such as subsystem A must send an acknowledgement to subsystem B within 5 milliseconds of receipt of the message. Okay, that's an example of a temporal requirement. So here we have R, which consists of R sub 1 through R sub n. That's the set of all the requirements of our software system, and there are n. T is a subset of R, consisting of T sub 1 through T sub m temporal requirements. P is our set that is defining our sub-processes, and it's P sub 1 through P sub k. We assume that for each of these steps, P sub 1, where I goes from 1 to k, we can accomplish this by using any of the J sub I techniques that are available, and we have those defined in a set C sub I, which consists of P sub 1 through P sub j. And finally, P sub k, that's going to be the specific technique that we select to fulfill the sub-process k. So moving on, continuing with our process specification, for us, we're modeling 4 steps of this temporal consistency checking process. The overall process that we're currently using, which I'll mention in a second, actually has 9 steps, but we're just modeling the first 4 steps. We're interested in the output and the quality of the output from step P4, and we call that O4, or output 4, because that's going to represent the quality for the overall process, as seen by the analyst who's getting those results. So we have our objective function here, which we call process cost, and of course, process cost, with process cost, less is better, so we would like for this number to be lower. And it consists of error leakage of P sub k plus wasted time of P sub k, where error leakage we're viewing as the number of relevant items at that particular step times some error rate. And the error rate is a function of the accuracy rate. So error rate plus accuracy rate is 1. Then wasted time, or WT, that's the number of relevant items times some cost rate. The cost rate is a function of precision, where the cost rate plus the precision is equal to 1. So I'm going to come back to this in just a second to show you our overall study design, but let me zoom in for just a second and continue on this consistency checking of temporal requirements. As you can see here, we've modeled these 4 steps, and we're showing the input factors for each of these steps. So in step P1, what we're doing is we're retrieving from the set R all of the temporal requirements. So we're retrieving T. So as an input, you can see that we take R, and then we take all of these different factors for step 1. The output is O1. We do the same thing for each of the other steps, P2, P3, and P4. Step P2 is where we retrieve any requirements related to those temporal requirements. So in effect, we take the temporal requirements and use those as our queries. We search again into the whole set R and retrieve things that are related. So when we get to step P3, we have the temporal requirements plus any other requirements that were related to them. And what we do then is we tag the parts of speech of all of those requirement elements. And then in step P4, we take the tagged elements and we apply semantic role labels. So at this point, we just label them as either being an agent or an action. So to move back to our overall study design, thinking about this subset of this consistency checking problem, we address it by using 3 different data sources. First of all, we address it by using data that we've retrieved from a literature survey. And I'll talk about that in a second. In the middle, we use simulated data. And at the bottom, we use data that we got from an actual study where we used our approach to consistency checking of temporal requirements called TEAL, or temporal action language. Now, I'll stop for just a second here and say that we were highly influenced and inspired by some work by Baker et al., which included Dr. Mark Harmon on that paper, where they were interested in the next release problem. So they were looking at a set of requirements and trying to decide which requirements should be implemented in the next release. They then defined this as a single objective and a multi-objective problem to try to minimize the cost but maximize the value that they would get in choosing which requirements should be implemented. They used simulated data, which they called synthetic data, and then they also used data from a real-world study. Then, of course, they performed a sensitivity analysis and then went on to use a greedy algorithm and NSGA2 and some of the tools that you all mentioned to continue on and evaluate this. But we were very inspired by their design, and that was part of the way that we came up with this design that we used. So now I'll move into those 3 different data sources. In terms of the first data source, it was a literature survey. So we looked in the literature and we came up with accuracy rates and precision rates from literature sources. This is an example for the data techniques, the techniques that can be used for steps P1 and P2, where there's retrieval. These are just a very small subset of some of the many information retrieval techniques that are available. You can see that on the far left column. Vector space model, LDA, LSI, and so on. Then each of the columns shows the features and the literature source and the data set. We also identified lower and upper bounds for these different data values. Next, we show some data for parts of speech taggers. Again, we found this in the literature. You can see there's many taggers that you might use. We gave the factor, the literature source, and then the data set. And in the paper, you can also see the similar table for the semantic role labeler. And I'll get to the simulated data in just a second, which was our data source 2. Data source 3 was our actual empirical study, where we were using our technique, the temporal action language, and we actually had to select, of course, different techniques that we would use at these different steps. So what we did here for step 1 and 2, we used vector space model with term frequency and inverse document frequency weighting. For step 3, we used the Stanford parser in order to perform our parts of speech tagging. And then for step 4, we used the Senna semantic role labeler. And you can see here, we show you the factors that we found in our study. The particular data set that we were using for that is the 511 system, phone system for the state of California. So we used a 4-step research approach. First step was we modeled our problem, which I presented earlier. The second step is that we determined the distribution of the accuracy rates and the precision for each of those sub-processes or steps, and then we used Monte Carlo to generate samples based on our 3 data sources. For the literature survey, we used the lower bound as our worst case, we used the upper bound as the best case, and then we modeled the uniform distribution. For that simulated data, which was similar to the synthetic data from Harman's work, we assumed a mean of 0.5 for all the values, and then we assumed a normal distribution and modeled that. And then for the last data source, for teal, we basically used those values from the empirical study, and again, we were assuming a normal distribution, and we used expert opinion in order to estimate our variance, and also what we saw others doing in the literature, which was basically using plus or minus 10%. And we wanted to thank our colleague also, Dr. Arnold Stromberg, from the statistics department at University of Kentucky, who helped us with this part. The next thing that we did was we generated scatter plots. And those we did so that we could perform trend analysis and also look and see that there weren't any errors in the model. And those scatter plots are in the paper. Then the fourth and final step of our research approach was to perform correlation analysis to rank our various input factors that I mentioned earlier and see how much they were contributing to our objective function. So before I go to the results of our exploratory sensitivity analysis, I thought it might be wise to step back and say, well, what might we expect? So think about our process. We have these 4 steps. Step 1 and 2, where we're doing retrieval of different elements. Step 3, we're tagging them. Step 4, we're doing the semantic role labeling. And then at the end, we have the analyst that's grabbing these results and working. One school of thought might be to say, well, even if the quality of steps 1, 2, and 3 are perfect, it won't matter if step 4 is very erroneous, because it could basically introduce so much error, it could largely influence this process and cause you to give the analyst erroneous data. So that would be a school of thought that would say the P4 factors will tend to be the most influential. A second school of thought, and this was the one that I subscribe to, is that P1 is going to be the step that really can get you into trouble. And the thought there is that if P1, for example, only retrieves, say, half of the elements that should be retrieved, when you move to step P2, you've leaked that error into step P2, and now at no other point in the process will you be able to refine those elements. So when you get to P3, you won't be finding related elements, and then you won't be tagging the elements, and then you won't be labeling the elements. So those are 2 different ways that we might look at it. Of course, one could also argue that you could also get to the very end of the process and the analyst doesn't even realize that there's many missing elements that they don't have, and that's unfortunately another problem. So let's see what we found out. We're depicting our results of our sensitivity analysis using tornado charts. The idea here is that you look at those ranked correlation coefficients and you're able to visualize their magnitude and their direction, so that they're either in a positive or a negative direction. So that's what we use here. This is the tornado chart for the literature data source. What we can see here is that the P2 accuracy rate was by far the most influential factor in the negative direction, followed by P2 precision, also in the negative direction. Then the next most influential factor was P1 precision in a positive direction. Now, what needs to be noted here is that none of these correlation coefficients are very large. The largest one is negative 0.087. Okay, so how about our simulated data? Here's the tornado chart for our data that we simulated around that mean of 0.5. What you can see here is that P1 precision by far was the most influential factor in a positive direction at 0.25. This was followed by P4 precision in the negative direction at minus 0.15, and then the others were all much smaller. Finally, we have this tornado chart from our teal study. What we can see here is that by far, P1 precision is the most influential factor, and it's in a positive direction at 0.35. It's followed by P4 precision, which is a much, much smaller factor in the negative direction. And then as you can see, the rest of the factors are fairly well down in the noise. So if we step back and we look at the full ranking of these factors based on the 3 different data sources, we can see that, for example, for literature, P2 accuracy was the most important, followed by P2 precision, and so on. We can see here that we don't have P4 showing up in that list until closer to the tail. But we do have P1 precision shows up in position number 3. If we look at our simulated data, we can see that we have P1 precision followed by P4 precision followed by P4 accuracy rate. So that actually lends some evidence that both of our schools of thought might have been correct. And then if we look at our teal study, we see that we have similar results to the studies for the simulated data. And in fact, we can see that these last 2 data sources share 2 items in common if you look at just the first 3 positions. The P1 precision and the P4 accuracy rate both appear. In general, we felt that this shows that this accuracy rate and the precision can influence the quality of our overall process. But it's clear that we definitely need to undertake some further work. Specifically, we need to do some further analysis and refinement. We really are just scratching the surface here, and we need to account for some of our threats to validity. Threats to construct validity include the fact that we only modeled accuracy rates and precision, and there's many other factors that could and should be modeled, and in fact, it could be the case that these results that we're seeing are not because of the accuracy rate or the precision, but rather are because of the data set or the domain or some unknown factor that we haven't even considered yet. We also use quite a few simplifying assumptions. One of them I mentioned was that we only looked at the first 4 steps of this consistency checking process, and I'll talk about simplifying assumptions a little bit more in future work. Some threats to content validity included the fact that we basically did a convenience survey. We definitely did not do a systematic literature review. We used just some generic keywords to search to be able to find places in the literature where they have published their accuracy of their techniques. And we then got those lower and upper bounds, which we used as our worst case and best case from the literature. And then, of course, we absolutely have a threat to external validity in that we looked at just one example of these many different processes that I mentioned to you all, which was this consistency checking for temporal requirements. Now, there definitely has been some related work in this area. So, for example, there has been some work on looking at software engineering processes. Lee et al., they looked at an SVM model, and I also mentioned the work by Baker et al. Earlier that Dr. Mark Harmon was on. The difference between their work and ours is that they didn't step back and look at these processes as basically being a collection of related steps or sub-processes. There's definitely been work in process modeling, and I give as an example here some work by Algeria et al. They came up with a tool called Avispa that basically lets you use their language for defining different process models, and those are SPEM compliant process models. The hardware modeling I mentioned earlier, this work by Ni et al., where they basically were trying to look and see if a variation in the process would change power leakage as opposed to us worrying about error leakage. And then there's definitely been other consistency checking work that's been done. For example, folks have used linear temporal logic, folks have used temporal action logic, and then, like ourselves, we use answer set programming. Now, one of the reasons that we chose to use answer set programming and design our own intermediate language is we found that LTL and TAO made it very difficult to express requirements such as the one that I mentioned earlier, where you have something happening within so many milliseconds of something else. So to wrap things up, we definitely have some future work to consider. For example, we have those simplifying assumptions that we use. And one example is this. For the parts of speech tagging step and for the semantic role labeling step, we assumed that for any given requirement that we tagged or labeled, every tag was correct or every tag was incorrect. Every label was correct or every label was incorrect. So we need to basically loosen that constraint. Second of all, we need to look at modeling the impact of having a human analyst in the loop. Third, we definitely need to undertake a systematic literature review as opposed to our convenience survey on the different techniques that we'll be examining. And basically, in general, the reason that we need to undertake all of this future work is we want to be able to answer this question: how can we know which techniques to select for each of these different sub-processes or steps? Thank you for your time.
Time for a few questions. So I'll get us, go ahead, please.
So you mentioned data now and the work of Mark Harmon on the next release problem. And one of the criticisms of some of the formulation of the next release problem is it assumes independence of, say, the cost and benefit of each component, rather than saying, well, actually, if you do all these together, the benefit is much more and the cost is less. And I'm wondering if a similar effect could happen with the accuracy rates, precision rates, is that if some certain combination of process choices, could there be sort of a dependence effect between those? Or could they still be, is this so accurate tomorrow completely independent?
I think that there could be dependence. So I hadn't thought about that, but I'm trying to think of an example. So, for example, suppose that you have, I mean, this is totally made up, okay, but suppose that you have some downstream step or process, it could be tagging or labeling, that works best on certain type of data. And if you have a weak technique up at the top, and it's the case that the type of data that the taggers and the role labelers love is unfortunately the type of data it's bad at retrieving, then yes, you could imagine that you could put together your perfect storm set of techniques where you basically make all the wrong choices. So I think that yes, there could be something to that.
Other questions? So I had a question about this one. So I had a friend and hopefully a future collaborator bring up this exact issue not too long ago. And he made the point that several of the tools are configurable to balance precision versus recall. And he asked me this question. I didn't have an answer for him, so I'm going to kick it to you. Maybe you have an answer.
Sure.
Why not just set all of the approaches to maximize precision at first, and then, based on the results at the end, start with the last one and before, and slowly tweak recall up until you're satisfied with each one? Because his point was that the imprecision at the beginning was liable to make worse results later. I didn't have an answer either, so.
So I think maybe a problem with that might be that in some of our applications, recall is far more important than precision. And some studies have shown, at least anecdotally, that humans are better at vetting results that are given to them and are able to weed out false positives, but they're not so good at going and finding results that weren't presented to them. So I have to think about that. On the other hand, it's definitely the case that if you return so many false positives, the human will basically get frustrated and lose confidence in your tool, and then they might just stop using it altogether. If you started by optimizing precision, you could certainly imagine that I could return to the user 5 results, and they're very precise, but I should have returned 5,000 results. So then one has to ask about, I go to what Lionel was saying about the practicality of it. But I think it's a very interesting suggestion and maybe worth looking into.
Sure. Other questions? Okay, in that case, let's thank our speaker. Please step back. Okay, while he gets logged in, our next speaker is Timothy Dietrich from DePaul University. Good morning. And he will be talking about improving traceability queries. Please.
Morning, everyone. Thank you for attending today. Today we're going to be talking about something better trace queries, which has been a focus of our research and our research group for years now. It starts with software traceability, and our definition of software traceability is the ability to relate any uniquely identifiable software engineering artifact to another artifact, maintain those links and that kind of connective tissue between those artifacts over time, and use those trace links. Oh, sure. I'm sure there are many people that I know that would probably not hear my voice, but how's that? Okay. So software traceability, for those of you who are not familiar with it, is the ability to take software artifacts and interrelate them to other software artifacts, effectively creating a trace. We then actually focus also on maintaining those trace links over time, so we're able to use them to show that the resulting network of trace links is able to answer a whole bunch of questions about the software product and its development process. And PowerPoint just got a little jump happy on me. A couple of areas of note where this is extremely commonplace and extremely helpful, include regulatory compliance, impact analysis, safety analysis, even design rationales. Anything you're designing, a piece of software, you have requirements. They typically have to get tied back to some portion of validation. So being able to tie these artifacts together and show that, okay, now that the software is implemented, yes, it satisfied these goals, these requirements. Is where traceability really stands out. Further, when you're developing software in certain industries and for certain companies, it's actually mandated, to show that you have, truly crossed the threshold of meeting a regulatory code, for example, or in the case of some process improvement initiatives that you've actually stipulated, this use case, for example, has been implemented in the software. Here's exactly where it is. So it acts as a formal dictionary to basically ease up the answering questions that typically come up after everything's done. Everybody's patting themselves on the back. Okay, but did it solve everything that we had talked about 6 months ago, 6 years ago when the project first started? The biggest problem with this, though, is as projects do grow and as projects do progress, the number of traces that are created quickly becomes unmanageable. It grows exponentially with the number of requirements and the number of design techniques that you end up implementing. So maintaining that dictionary is just a Herculean effort. Now, there are several approaches available to help automate this process and to help keep it healthy. We had just heard a bit about VSM and using the TF-IDF approach. Under the vector-space model, LSI, LDA, they've all had success in basically taking the text of one artifact and matching it against another artifact to maintain or to create a trace like to begin with. Our overall research is actually focused on taking many different types of components, from pre-processing all the way down to matching, all the way down to post-processing, and looking at each data set and trying to figure out what is the optimal configuration for that data set in terms of being able to help automate, create these traces. As you can see, there are a lot of different variations that we can go through here. We've recently just published a paper, we being my research group and myself personally, using a genetic algorithm to actually help search through this much more quickly. Now, on the face of it, just the numbers that are being proposed here might not look like a lot, but remember, you're running against incredibly large data sets, so time is precious. You can't do an exhaustive search on these in any kind of remotely easy sense. The vector space model, which many of you might have used already, is a great model for comparing text data against other text data. What it effectively does is it breaks each document within the dictionary down into its base term parts. Those components can be stemmed, they can be stopped, they can be transformed in a multitude of different ways, and then compared against each other for similarity. And then there are also multiple similarity constructs that can be used. At the end of the day, when you're looking at a query that actually does have matches, you're looking at the average precision that the VSM engine is using to bring those up. You want to see all of the relevant queries be brought to the top as quickly as possible, and therefore making the average precision of a great metric for a single query. But document sets have multiple documents, and therefore evaluating the effectiveness of any algorithm over the entire data set, we use mean average precision, which is basically just the average of all of the individual average precisions across the data set of documents. The research that we have going that I'm presenting today, we had used 4 different data sets. And we always start with a baseline mean average precision. We want to know what is the bar set at before we do anything else. So that way, are we harming it? Are we doing any good? Are we moving it in the right direction? This sets the bar for deciding whether or not any kind of improvement has been gained. So in improving these queries and improving the average precision, we've already done a bit of research using human users to go in and manually modify queries. One of the limitations of VSM is that it doesn't do a lot of good work jumping contexts. So, where a human might say, this term is actually associated with that term, that's not actually built into the VSM model, as it's implemented in its standard form, using the TF-IDF. But the user, however, can take a look at this query and that query and say, yeah, those two are alike, or they're not alike. Mark it and move on. They can also go through and take a look at the document and say, you know what, these words aren't really relevant. They're in there because it's part of the requirement or part of the specification, but they don't really add a lot of value. Here are the key terms. Also, missing terms. Why isn't this term in here? This is really what this requirement's about. Maybe it's in the title, but it didn't make its way down into the document. Allowing the manual user to actually go through and make those modifications ends up showing a substantial amount of improvement, as shown in the DQM, which is a directory modification that we've used for manual modifications. Now seeing this, we started to ask ourselves the question, hey, how do we make use of that? So now that the human user has actually spent all this time and energy going through and making all these modifications, well, that's all well and good, and yay, it's improved the average precision, but we still have to have somebody sit there for so many hours. So we came up with the idea of, okay, let's take a look at the patterns of what the human is doing and let's see if we can model those out so that we can start to make the next one a little bit better, and start to be predictive in suggesting what the modifications for the next query should be. And we do that by basically taking a look at the modified query and then developing what we call our transformation rules. So on the left-hand side, on the precedent, we basically take the publication of all of the existing terms in the query, and we just list them out. And then we multiply them by any of the resulting actions. So we remove the word remote here. So that is going to show up many times. We add the word display. You do that across every different query, and then all of a sudden you end up with this really nice data set of here are all the transformations and here are all the patterns that seem to be associated with those transformations. Let's apply them. So having found success in being able to apply those transformation rules when they were derived from the manual query set, the next natural question, especially being software engineers at heart and wanting to automate things and just pressing one button and go and have it do it for us instead of always having to bring in bodies. Can we automate this? Is there anything users doing, creating these transformations that an algorithm can't do? And that was really the core part of the research that I'm presenting today. So the first step is how would we do that? Now, the automated query modification, takes the exact same approach that we did on the manual modifications, but it optimizes it. It actually looks for an optimal average precision on a document by document basis by going through and systematically removing words, adding words, and finding, okay, here's the optimal combination of additions and subtractions that gives us the highest average precision. Now, by doing this also generates us a much substantially larger set of transformation rules than what we had seen in the manual modifications, because we're also seeing many more modifications come through from that automated process. So, taking a look at the Pareto diagrams here of just the number of modifications and then the number of documents that were impacted by that. On the manual side, we can see, okay, modifications were made, but they were typically, plus or minus 6 modifications, and certainly, we're well over the 50% mark on a cumulative distribution on, we're around 10, being the max. But a lot of them just had one modification. Not a lot of data for us to then say, okay, let's go in and data mine, what that transformation was. On the automated side, however, we see that distribution, start to slide out a little bit further. There are substantially more modifications that are being made to the documents. One notable difference that we saw just right out of the gates was that we were adding on average 2 terms to every document to help improve the average precision, versus the less than 1, the 0.67, that we were seeing on manual side. And this gets back to human versus computer. I sat there with the software myself. I didn't want to have to think. I wanted it was so much easier just for me to point and click and remove words than it was for me to say, what other words should I be adding? And then it's trial and error, and it takes a lot more time and a lot more effort. The computer doesn't mind that. So basically a transformation. What do we do with all of these rules once we have them gathered up and organized? The first step is to create the permutation of all the rules. search for the rule set matching. So we have a new query that's presented to us. We break that down into all the different patterns of terms that exist within that query. And then we search through the transformation rule set for, show me anything, within the rule set that actually matches these words. Bring those over, and then based on, a handful of thresholds, apply it to the query. So, as we had just seen, in the previous queries, the word image. Anytime the word image appears, it appears in a new query, and that means that we're already going to be pulling down new rules to apply to that query. In the example that we give here, ABC, FGH, J, there will be the rule ABC indicates that we get rid of C. Okay, so let's do that. And then we move down to the next one. FG is a pattern which exists in the query, indicates that we remove F, we remove G, and we add N. So adding these rules all the way through, and at the bottom gives us just A, H, J, and N, as the terms that are remaining based on what was added and what was subtracted, simply from the rules that were mined from all the other queries that had been modified. Yes?
The result history
The result history dependent on?
which rules are present.
It can be, but it doesn't necessarily need to be. So even if a rule such as FG removes F, came after FG removes FG.
What if you didn't remove C and then you had to remove C?
So you always maintain the existing the original query set. That is what actually pulls the rules down first, and then you apply all the rules. So even if C is modified before you get to the rule that had actually pulled C down, that rule is still in the data set for it. But that was an excellent question. That was actually one that we had to deal with, kind of early on, was as you're modifying it, you're also kind of effectively modifying the transformation rules. Because if you're adding a term, should you go back to to the trough and say, well, now that F's a new term, should we pull down anything with F as well? And the answer to that one was no. That was not an approach that we decided to take because there was too much of a dynamic nature in there where you could actually get stuck in a loop of every time you're adding something, you're constantly creating this.
There is a literature.
Is there
Yeah, because
a topic or a term?
some of the object-oriented databases have rules.
Just like
Now, this
that.
goes back to the 80s.
Right. Well, maybe we can talk about this after. I would love to hear. Great. I love hearing about things that I've done before that I can learn a little bit and apply going forward. But to answer your question, we do not go back and once the rule set is pulled, that is the rule set that is being applied. Now, we have all these rules, and we have a large number of these rules. How do we actually differentiate which rules really should be applied, which ones are applicable, which ones are relevant, versus which ones are, in data mining, there's a lot of literature on what are called spurious rules. Is that me? Okay. So elimination of these spurious rules, they show up because they're highly frequent, they occur all the time, so support and confidence don't actually filter them out very effectively, but they tend to add a lot of noise. They don't add value, and sometimes they actually detract from value. So we've actually created two new filters here too. One is a term-based filter, which is very similar to the common use of stop words, except that we've used a statistical distribution based on the terms IDF. We say, okay, if it's in the first quadrant, great. If it's in the top third, great. If it's in the top half, top 75%. How specific does the term need to be in the dictionary in order to be included in the rule? And then the second one is rule-based filters, just simple length of rule. one-word rules, tend to be a lot more common than rules that actually have 2 or 3 terms, or even 4 terms. And therefore, does that specificity actually end up, showing some promise of helping us get to the rules that really should be applied? In our research here, what we've done is we actually went through, we ran through every combination of each of the different values against each of the different values for all the filters. So we ended up with a complete set of, here is where things have ended up. But as you can see, by doing that, you end up with the ability to go through and figure out what is the optimal set of parameters to use. So we use 4 different data sets, 2 of them from industry, which are under NDA right now, but we were lucky enough to be able to use the CHIP database, which is a healthcare data set, and the CM1 data set from NASA. These were selected because some of them are larger, some of them are smaller. They had a couple of different demographics. We wanted to make sure that anything that we were going to end up presenting was going to end up being applicable to many different data sets and not just one. As I said before, we use the baseline mean average precision as kind of our threshold. Now the artificially created, the computer created, AQN mean average precision score shows us, okay, here's the optimal, here's the best map score that we could get, letting the computer make all the modifications. And as the research indicated, there is definitely a gap between the baseline and the AQN, which means that if we proceed correctly, we should be able to fall somewhere within that gap, showing improvement from the baseline by learning from the AQN queries. The initial transformation query experiment uses just support and confidence as the 2 base filters that are most commonly used to filter out rules. And then the second experiment adds in the term-based filter that I just talked about, as well as the rule minimum filter, or the word minimum filter that I just talked about as well. We separated those 2 out as confidence and support are commonly held as acceptable. We weren't sure what value was going to be added or not going to be added by the addition of those last 2. So we didn't want to muddy the waters and say, okay, well, it could have been for this, it could have been for that. But it turns out, the comparison ends up being quite interesting. On all of the data sets, we were able to improve over the mean average precision of the baseline, but to varying degrees. As you see in the CHIP database, we do substantially better, about climbing halfway up, the maximum mean average precision that we've ever seen on the AQM side. On the CM1 data set, we are just a smidge above baseline. Now, the CM1 data set is a remarkably small data set, so that's not actually all that surprising. But on the industry data sets, we do end up, seeing another increase over here, and then just kind of a minor increase over here on the industry 1 data set. The next couple of slides are going to get into this in just a bit more detail. So if I was looking at that previous slide, I'd be like, okay, those are great numbers, but where are you getting them from, right? So what we've done here is this is confidence and support only. We've taken actual confidence levels. Note that the different support levels here vary depending on the data set. We've tried to take ones that were kind of most interesting and most indicative of what we were seeing. Confidence, still definitely, ranking highly as improving the average precision. So, we've kept that as our foundation all the way through. And support, not really adding as much value here as you might see in other DSM experiments. Now, adding the rule-based filter. So now remember, this is the rule minimum, rule length of 1, rule length of 2. We actually see that this sometimes adds some value, sometimes subtracts some value, and sometimes does both depending on the confidence level. So this was a little bit surprising until we got to the term-based filter. Now, one of the things that we inevitably run into, while we're experimenting is, well, what do you mean there were no rules in, IDF2 at a certain support level or any support level? And, that was the case that happened with Industry 1. But with Industry 2 and CM, what we end up seeing is taking the top 50% of that cumulative distribution of term IDFs actually does improve, substantially improve the mean average precision. Now, going back to the rule minimum, which didn't perform well on its own, when you actually start putting the two together, the rule minimum with the IDF-based filter, the rule minimum does start to augment the results that we're seeing on the term-based filter alone. So in summary, what we found is we found an algorithm that actually works incredibly well on taking a set of queries, automating the modifications, so eliminating the manual and intensive and costly labor, but it still requires a training set. So one of the challenges is the larger the training set, the better. The other challenge is, as with so many experiments, you can end up with great results, with a very specific set of parameters for your inputs. But how do you know what those parameters are? So this is where a lot of our GAB-based research is being focused on right now. But given the success that we have seen here, we know that it does work. It works well, and it's going to be added to that larger diagram that was shown initially as to here are some of the components that we're using to automate traceability. And possible next experiments. Can we generalize the rules learned from one data set over to another data set? Maybe industry specific, maybe language specific. There are a bunch of different ways to approach that. What is the minimum recorded size of the training set to be used? So we had one remarkably small data set in here that was specifically selected because we wanted to see was there a minimum there, and it didn't perform as well as the other data sets. And then also, should we explore the term-based and the word-based filters a little bit further, maybe extending them out to task 1 and 2, and on either side, and see if we get better results from there and moving spurious rules. So I know I'm close on time here, so I'm going to open it up to questions at this point.
Questions, please. Time for a couple questions.
Well, that was a lot of information. Somebody has
Sure.
to have some question on that, right?
Thank you, I really enjoyed it. Let's see, I think I'll jump to slide 11, if that's okay. I had a
Slide
couple
11.
questions, but
Oh,
I can
absolutely.
ask you about it at lunchtime. Slide 11, what was my question? Oh, so my question here was, if you generate basically all possible permutations of these modifications by looking at, say, WordNet, I can see here that you're looking at synonyms and other, or if this was modeled from your manual query modification studies with humans, or if you're just...
So we're actually not using synonyms at that point. What we are using is strictly the words that are included in the query documents themselves in each of the data sets. So we're limited, by not having to go out to a WordNet, which is, a very large, dictionary of words.
Okay, so then how did you, in query 1, how did you come up with add scan and add display? How did you come up with those suggestions?
Good question. So we do have the existing traces to learn from. So on the leap one out approach, when we're looking for words to add, we have a set of terms over in the target dictionary and a set of terms over in the source dictionary. And that is the superset of terms that we're looking at here, in terms of, of words that can be added. Then obviously the words that can be subtracted have to be existing in the query itself to begin with. But any of the words in either corpus effectively, are going to be added as long as they're not already pre-existing. But then we don't go out, the whole scope. And that makes sense because adding a word that's out of the scope of the target corpus isn't going to add any kind of value in terms of average precision because it's never going to have a word hit on the opposite side.
Okay, so we're a little short on time. If there are other questions, please come talk to them after, talk to the speaker after the fact. We had a couple of questions during the talk also. So let's thank our speaker. Our next speaker is Thianniwet. He will be discussing the complex feature models and how to optimize.
Oh, yes.
So I do apologize for the between sound in the corner. We have to have some kind of technical glitch. But please go ahead and speak over it. Don't let it bother you.
Is it good?
The cell phone is causing a problem. Oh, well, what is? Please.
So did you hear me well? All right. So hi, I'm Thammasak from University of Nebraska-Lincoln. So today we will talk about our SPLRevO. Reverse engineering feature model from SPLRevO line. So first of all, let me give you a little bit about the motivations of our research. So suppose that we are a car coming in maybe Detroit, and it turns out that several cars may share the same software components. Like I showed you the table of contents here. It showed the set of varied configurations. Like maybe all car use the horsepower control, and maybe some car has the air conditioner controls. And somehow we want to maintain the features, and also want to test all of the products in our company. And that we might need a software product line engineer. So the software product line engineer is the software development paradigm that developing the software that share a common set of features. And we have a feature model that describes the whole set of products in the family. So the feature model consists of two parts. The first is a diagram that shows the relationship between features. For example, like the transmission horsepower of the engine has the solid circle under the car. That means these features are mandatory when we build a car. And the air conditioner and cruise control have an open circle. That means these are optional. We can select or deselect these features. And for transmission, it has the open arc. It said that it is alternative feature group. So it has auto, manual, so we can select one of these under the transmission. And for the engine, we have the solid arc. This means we can select one of these or both of them at the same time. And the latter pass is the cross-free constraint. We show that that is the additional constraint that might be happened. And here we show the required age from automatic and air conditioner. That means the air conditioner is the prerequisite for automatic. And here we show the exclude states. So the manual implies non-cruise control. That means these features cannot be selected together. And there might be other more complex constraints that can be added later on the diagram. And that might not be shown in the diagram. And why we need the feature model. So as I say that the feature model can explain all the entire products in the family, and it provides the abstractions. For example, like we have 1,000 products, and we have to have a single notation for describing the whole set of products. So we need that feature model. And when we need that feature model, when we have that feature model, we can use it for other analysis. Like we can use it for supported testing in order to reduce the combinatorial testing. We can use it for maintenance, for target marketing, and provide more readability. But however, it turns out that the feature model not always exists. Like in some legacy systems, that doesn't have the feature model. So in that way, we might need to reverse engineering the feature models, maybe from some artifacts like the source code, or from some documentations, or from the set of value configuration. And recently, there is an ETHOM framework that do the reverse engineering feature models using the evolutionary algorithm, and it takes the valid set of configurations as an input, and it uses genetic algorithm to find the feature model that describes the exactly same set of products as the input. And in the evolutionary, we find the feature model, and we can ask a set solver to generate the set of product that the feature model can describe. And we want to, and that is on the left side. And we have the input as the desired product, as we want to cover. So we want to maximize the intersections, that is the matched product between these two sets. And you see that we might have some dangling product on the attributional side and in a missing product as well. And that we don't need. So the solution of the evolution algorithm is to find the exact same set of products. Okay? And currently in ETHOM, there are 3 finesse functions, but it turns out that all 3 finesse functions have some limitations. So let's take a look on the first one, called FF-relax. So FF-relax here, it maximizes the number of matched products. But we do see some limitation here, like here in figure A, we match H-team. Suppose that we have H-team design products. And here we match H-team, that is the maximum one. But it turns out that we have 6 additional products that we don't want. But now, relax return the maximum. So we said that this one, relax return the incorrect solution. And the next one is kind of know that issue. So it put another conditions like these 2 sets have to have the same cardinality. Otherwise, it returns 0. And for this example, we have 2 sets, 12 and 18 of cardinality, so it's different. So in this case, strict return 0, but we do see that it has match 12. So we say that we might need something more than better than 0 in order to guide the search. For the last one, the min-diff, instead of maximizing the match number of products, so they minimize the additional and missing products. And here we have match H-team, but we have 6 additional products. So the min-diff doesn't aware about how many match we have. So min-diff just return 6. And for the figure B, we have 6 dangling product on the missing as well. So the min-diff also returns 6 as well. So as you see that figure B and figure C, we have the same value for min-diff. So, but you will see that in the figure C, we have more match. So we might need to differentiate these 2 scenarios. Not only in the finesse function, we find some limitations on their chromosome as well. Like when you're dealing with multiple feature groups. So in the gene of a chromosome in ETHOM, they have tunable relationship and children. When we encode the diagram, we encode that as the DFS ordering. So let's take a look closer on where we might have some problems, like the feature engine, the feature 4. The feature 4, we have mandatory relationship from car, and it has 4 children, but actually it has 2 distinct alternative feature groups. But in the gene, it just only have 2 tuples, relationship and the number of children. So we lost the information about the set in this encoding. So the encode might have just only M4, and all 4 children has alternative 0, 0 children. And when we decode it back, for feature 4, M4, M is mandatory, so we have 1 feature as mandatory, and 4 are for 4 children. And when we fill all 4, you will see that all 4 children has been divided into a single feature groups. So it's different than the original one. And we do see the existing of the multiple feature groups in the real product line as well, like in the Splot website. That is the online repository for software product line. And okay, and the next part is the constraint. So the constraint in ETHOM, the gene consists of 3 tuples, type, origin, and destination. And it only supports for the single constraint, the simple constraint. So the simple constraint means it only supports type, only support the type of requires or excludes. And the origin can be a single feature. The destination can be a single destination. Like this one, automatic implies air conditioner. So we can encode this as R19. But how about this one? Gas 1 or elect 1 implies manual. So right now on the left-hand side is not a single feature anymore. So it is an expression. So ETHOM doesn't have any representation for this. And we do see the existing of this complex constraint in the Linux system as well. And finally, we said that we need a new some representations for a feature model. So our contribution for this research is we propose the new framework called SPLRevO, software product line reverse engineering optimization. We use the genetic algorithm to find the feature model. We have a new design for the chromosomes that support multiple feature groups and complex constraints. We have a new design for the fitness function that have more accurate. It's called FF validity. And in chromosome, because we have a new representation, so we have new design for chromosome as well, for crossover. And for the mutation, we add more operators on that. And we validate our FF validity and also SPLRevO. So let's take a look on our SPLRevO. In our SPLRevO, we have new fitness function called FF validity. So compare with the MinDiff in ETHOM. So the MinDiff will minimize the additional and missing product, but it takes these two as the same weight of penalty. So for our FF validity, we put a small amount of penalty on the additional products, and we maximize the match product. And we use the log2 to reduce the effect of combinatorial explosion on the number of products as well. And well, the solution should be the same scenario when we find the same, exactly the same set of products. So suppose that we have 18 desired products that we want to cover. Right now we have exactly the same set of products, so if a validity, we return 100. And for the figure B, we match 18. But we also have 6 additional products. So we put some small amount of penalty on the addition, on the additional products so that the availability become 93.4 in this case. But for the min-diff, in this case, it doesn't aware about the match product, so it just returns 6, right? As it's shown already. For the figure C, so for the figure C here, we have the min-diff that returns 6 as well. But for our availability, we know that we have less match, then we have the lower value for that. So when we compare these two scenarios, the min-diff can't differentiate these two scenarios, but we can. So I think that we have done a better job this way. And for our chromosome representations, I like the EDOM that encode each feature in a chromosome. So we encode each relationship in the diagram instead. And when we're dealing with the multiple feature groups, we decide a gene that consists of 3 tuples, set of children, parent, and type, where type we can support IRD, mandatory, or XOR mutators. So let's take a look closer on the engine that caused the problem in EDOM. So right now we encode each relationship. So we have gas 1, which is the arc from engine. So we have gas 1 implies engine irrigate. Gas 2 engine irrigate. And then for the feature group, we have this. We have gas 1, gas 2 as a feature group implies engine and XOR. And you will see that we encode that explicitly from the structure of the diagram. So we don't have that problem of losing the feature group information. So then we fix this problem. And for the cross-free constraint, when we're dealing with the complex constraint, we illustrate that as the expression 3. And we encode that for each expression node. So we have 4 tuples for the gene, type, feature name, the pointer for the origin expressions, and the pointer of the destination expressions. And then by doing this, we fix the problem of the complex constraint in this as well. And for our crossover, because we have a new chromosome representation, so we design a new crossover. Unlike the EDOM that doesn't cognition of the relationship between features in the diagram, we do cognition the relationship in the diagram as well. So in our crossover, suppose that we have a source parent P1, and we have a target parent P2, and we want to transfer the relationship from the source P1 to P2 in order to create a new offspring. We randomly pick one feature, and then we transfer the relationship under that feature into the target P2, and we have a new offspring. And you can see that we can transfer that relationship to the next generation. And for our mutation operator, we have 10 mutation operator right now. We have 5 for diagrams and 5 for constraints. And the rate operators exist in EDOM framework as well. But for other operator, we have that before because we have a new chromosome representations. And so let me just give you one example of our mutation operator. Otherwise, we might have a lunch late. So this is the complicated operator for the feature diagram. We believe that by having more feature groups or adding more feature in that feature group will make the feature graph, will make the diagram more complicated. So in this case, we randomly pick one mutant, like the relationship from F2 to F7, and we want to mutate that by adding other features under the feature F2. By adding one feature under the F2, we need to confirm that that feature should not be its predecessor. Otherwise, we will cause the cyclic problem. So we randomly pick F4. And we did select that from its parent. And then we add that to F2 in order to create a new few groups. And that is the complicated one. And for the rest of the mutation operator, you can find that in our paper as well. So in our study, we conduct an empirical study to validate our F validity and SPLRevO. So we asked two questions. The first is, how does the FF validity perform compared to the existing ethon phenotype? And the second is, what is the impact of our new chromosome representations and also new genetic operator that we added in the SPLRevO? So in our study, we used 99 fusion models. So 91 fusion models from a Splot website, and it has been used in the ethon study as well. And we have 7 Splot models. We randomly select that and mutate that for higher complexity. And we use one complex model from the study of Shade et al. 2011. And we do categorize all models into 4 categories: small, medium, large, and complex, to see how it's different. In our study, we have a precision recall and F1 measure as our metrics. So we use F1 measure as our main quality measure that's balancing the precision and recall equally well. And now I show you the result of the F1 of all models. So we run every model's 10 runs, and then we plot the box plot. So the red box shows the result from ethon, and the blue one shows the result from our SPLRevO, and we plot that for each finesse functions. The first is the FF lax, and FF strict, and min-diff, and our SPL FF validity. And we do focus on the red box, which is the result from ethon. You see that our FF validity performed the best. And when we compare each finesse function within our SPLRevO, like the first one, the FF lax, you see that the FF lax doing slightly worse in our SPLRevO, and for a strict as well, and for the min-diff as well. But we do see that for our FF validity, it performed the better. And we see that the combination of our new finesse function FF validity and our SPLRevO, it performed the best. And when we focus for each categories, like the small, we see the same trend. But there are some slightly change, like in the horizontal bar. That means this is slightly changed, but it's not significant. Like for the result of min-diff and FF validity in our in their ethon framework, it shows slightly different. But FF validity also performed the best. And for the medium, you will see the same trend. And for the large here, the best is within ethon framework, but we do see that it's not significant. We run the statistical analysis, said that confirm that it's not significant. And for the complex model, you also see the same trend as well. So when we turn to the time consumed, we see that for the FF lax, it's the fastest one. But we do see that it stopped early, like it returned the incorrect solutions, and it can't improve in the finesse value. And for the FF validity, we say that it runs a long time, but it keeps converging. So in the summary, within ethon, we say that FF validity showed the promising result on the F1 measure, but except the min-diff on the small and complex model. And for Q2, within our SPLRevO, we see that FF validity performed better But for the EDOM, existing fitness function is still was some selected work, especially on the Wenbin. In conclusion, so we built the SPLRevO, reverse engineering the feature models that improve over the EDOM. And we have a new fitness function. We have a new chromosome representation to support the complex constraint and multiple feature groups. And therefore, we have a new evolutionary operator as well. And we say that with the combinations of AV validity within SPLRevO is produce the best F1 measure. So now for field work, we might study more about the time effectiveness trade-off for each fitness functions. And we will perform study for more complex models as well. And we will investigate a multi-objective approach as well, because many research in this conferences and that's all.
I've got a question. Back on slide 13, where you were showing us the new chromosomes.
Slide 13.
Actually, I took a note from my question as to paying attention to the actual slide. So when you're looking at R10 through R15, and say R13 is selected, right? So we have electric engine, it's part of the hierarchy. How do you then enforce that the rest of those chromosomes are not selected then? It seems to be kind of a a problem that comes up over and over again when you're trying to include multiple features within a single chromosome. Is it a linear filter afterwards? Because it can't be electric one and gas one at the same time unless you're using, like an XOR or some other kind of operator, right?
I'm not quite sure for your question.
Sure. So if you select R10,
select R10.
how do you enforce that R13 isn't also selected as the genetic algorithm goes through its search?
Well, so this one we show how we encode the chromosome. So for R10, R10 is one relationship from the engine to the gas one. And the R13 also another another relationship as well. So we encode that too. This thing here. So
but once it's encoded, it runs the algorithm using that feature, right? So R10, it use the feature of gas one. But how do you prevent it from also using like electric one if that came back as after the crossover or something?
Okay. So you're asking like how to change this diagram in order to not allowing gas one and elect one
Right.
to select that together.
Correct.
So in that way, because this one showing the multiple feature groups, the feature group is the anonymous groups. So in that case, we might need to have a select feature for the gas, for the gas group, and for the elect group, and then we have the alternative group for that. That might enforce that constraint.
Okay. Perfect.
One quick question.
You said that you have 10 mutation operators.
Yep.
The question is that when you select an individual for mutation, so how do you select a single, do you apply a single mutation operator or you apply all of them? So it's the first question. The second is in what way you do that?
Okay, that's a good question. Thank you. So, because we have 10 mutation operator, 5 for each 5 for diagrams, 5 for constraint. So when we do the mutation, we do it separately. Like for the diagram, we randomly pick one of the 5 from this, and for the constraint, we randomly pick one of the 5 from that. But when you look closer in our table, you will see that there are some tricky as well. Like each operator can be applied to a different mutation point. like the complicated one, we can apply that for for every relationship. But for the simplify operator is somehow to reduce the number of feature groups. So it's only applying to the feature groups, not every relationships in the graph. So in that way, we need to have the applicable rate that kind of dynamically adjusts the probability for dynamically pick the mutation rate.
So that is the adaptive one. So that means that based on the situation, it selects one.
Okay, then let's thank all of our speakers, please. Now it's lunch.
It's time for lunch.
Oh.
Yeah, no, that's it.
If I would have had any idea that's what it was.
That was the